So this is lesson 2 of module 1 of G482, and this focuses primarily on Kirchhoff's first law and its application. So Kirchhoff has two laws that you need to learn about. Kirchhoff's first law relates to current, specifically the current entering a junction. Now the key idea is a really simple one, that when electrons or any other charge carrier enters a junction, they can't just randomly disappear, they've still got to be there somewhere. So Kirchhoff's first law is effectively the principle of conservation of charge, which is that the number of charge or the quantity of charge that we start with must be the same as the quantity of charge that we end with. But it's principle of conservation of charge related specifically to electric circuits. So this is Kirchhoff's first law. The sum of the currents entering any junction is always equal to the sum of currents leaving any junction. So, as an example, if you take a look at this circuit, we can work out the current at each of the resistors and the current entering the two junctions. So, if you think about this arrow here first, if we think about resistor X, well, resistor X has got 3 amps going through it. It's in this direction, so it's still travelling in that direction, so we've still got 3 amps. So 3 amps are going to come here. So resistor X has got 3 amps travelling through it. Now we can see here that going into junction S, we've got 4 amps coming out. Now at this junction, because the arrow is coming this way, if I sort of simplify this, we've got 3 amperes coming in from X. We've got an unknown quantity going in there, and coming out we've got 4 amperes. So we must obviously have 1 ampere going in. So the current going through Y is 1 ampere, and then you can see that the current coming in at this junction here at T, we know that 1 ampere is going there, so obviously the opposite direction going through Y must again, going through Z must also be 1 ampere. So the total current entering this junction is 2, and the total current entering that junction is 4. So you can see the answers there, just so you can check those. If we do another example, again applying Kirchhoff's first law, we've got 3 identical resistors. They're connected in parallel, and we know that the current at point E is 0.3 amps. So because they're 3 identical resistors, that means that the current is going to split equally down each junction. So D must also be 0.3. B again must also be 0.3. So we know we've got 0.3 going there, we've got 0.3 coming there, so that means that C must be 0.6, and again we've got 0.6 coming that way, 0.3 coming down here, so A must be 0.9 amps, okay, which must be the total current, and you can check the answers there. This one, what now happens in this case is that the student has connected the ammeter in parallel incorrectly, and the ammeter is reading a current of 0.4 amps. And the question is, what would the correct reading be if they connected the ammeter in series? Now, there are a couple of assumptions in this question, but the key idea is that because I've got a parallel, the current must split. And so we can make the prediction that I'm going to get a total would be 0.8 amps that's going in. Now the assumption that we're making in that case is actually that the resistance of the ammeter is in fact equal to the resistance of the fixed resistor. Now clearly that's not true, because we know an ammeter has negligible resistance. So in reality what we'd get is that almost all of the current would go that way through the ammeter and would not go through the resistor. So So that's the main assumption that we're making. So here's a couple of simpler examples. So I, in this case, we've got 2 coming out of there, 1 coming out of there, so we must have 3 amps going in. Another example, this time we've got 0.5 basically plus 0.7, so that's going to be 1.2 amperes. And in this case, you've got to look at the direction of the arrows a little bit more carefully, because we've got if you look at what's coming out of the junction, which is that way and this way, we've got a total coming out of 4.5 in the 2 directions. So that meant we had to have 4.5 going in. So if we've got 2 going in there, that means we had to have 2.5 amps going in at that point. Okay, which you can see there. And one last little problem. When we've got a variety of different components this time, we've got fixed resistors, we've got a variable resistor, and we've got a thermistor. So component X is a thermistor. Remember, a thermistor, as the temperature increases, the resistance decreases. And then the current split, so the total current that we've got going in here must be the sum of these two, 31 milliamperes and 20 milliamperes, so it's 51 milliamperes. And then coming out of here, we've got 22 going in at this point, so that means that we must, obviously, because we know we've got to have 51 that comes out, we've got to do 51 minus 22, and so that is going to be 29 milliamperes. And then we've obviously got the difference here. We've got 31 going along there, we've got 22 that's going along the top, and so the one going through, current going through this middle resistor, I2, must be the difference between those, which is 9 milliamperes, and obviously you can see 9 plus 20 equals 29, so everything works. So key points to remember from this is Kirchhoff's first law. You could be asked to state it, which is that the sum of the currents entering a junction must equal the sum of currents leaving a junction. You can be asked which conservation principle it relates to, which is conservation of charge, and you can also be asked to then apply it as part of your circuit analysis. So it's really important that you've got a solid understanding of Kirchhoff's first law before moving on.